Hello everyone. Now I am going to present my seminar on the topic engineering stress strain curve. Through this presentation, we will explore how materials behave under tensile loading and understanding engineering stress and strain and study the different regions of the stress strain curve and discuss the mechanical properties and their engineering applications. Now let us see the um, engineering stress strain curve is obtained from a tensile test. This curve helps us understand how a material behaves when a gradually increasing tensile load is applied. From this curve, we can determine important mechanical properties such as strength, elasticity, ductility, toughness, and stiffness. These properties are essential for selecting suitable material in engineering elements. So, next we see what is engineering stress and engineering strain. So this is the specimen. In a tensile test, a standard specimen is placed in a universal testing machine which is also called as UTM. A tensile force is applied along the axial direction and load is increased gradually until the specimen gets fractured. As the load increases, the specimen elongates. During this process, we record the applied load at corresponding extension. Using these values, we calculate engineering stress and engineering strain stress by plotting stress versus strain. We obtain the stress strain curve. So now we see what is engineering stress. Engineering stress represented by the symbol sigma is defined as a applied force F divided by original cross-sectional area of the material or the specimen we require. Here F is the applied force and A naught is the original cross-sectional area and the unit of the engineering stress is Newton per meter square. The unit of the engineering stress is Newton per meter square, which is also called as Pascal. And it is important to note that in engineering stress, we always consider the original area, not the instantaneous area during the deformation. Next, we see about the engineering strain. Engineering strain represented by the symbol epsilon equal to ratio of the change in length to the original length, where L naught is the change in length and where del L is the change in length and L naught is the original length before deformation. Since strain it is a ratio of two length, it has no unit. Therefore, strain is dimensionless. Engineering strain helps us understand how much a material deforms when a load is applied. So next we see about the engineering stress strain curve. First, let us understand the graph. On the vertical axis, we have a stress, and on the horizontal axis, we have a strain. This curve shows how stress changes with increasing strain when a tensile load is applied. Now, first in this graph, uh, first we see that straight line region. Here, the initial straight line portion is called elastic region. In this region, stress is directly proportional to strain, which means it follows the Hooke's law. Hooke's law is a stress directly proportional to strain. If in this elastic region, if the load is removed in this region, the material return to its original shape. So here deformation is temporary. and the slope of the straight line, which means here it gives Young's modulus, which indicates the stiffness of the material. So now here you can draw a vertical line which denotes stress and a horizontal line x which represents strain. When a straight line gives when a load is given to a material, it elongates to some point. So this point is called engineering elastic strain. Here in this region is called elastic region. This is a temporary deformation. So when we remove the load, it regains to its original shape. Next, after the elastic limit, it is elastic limit, and this region is called plastic deformation. Here yield strength. After the elastic strain, the specimen goes to the plastic deformation. The material reaches its yield point. At this stage, plastic deformation begins. This means the material will not return to its original shape after the plastic deformation. For materials like mild steel, we can clearly see yield strength. Beyond this point, permanent deformation occurs. Here it is the yield strength. After this yield point, the specimen undergoes elongation. So this region is called plastic deformation. This region is called plastic deformation. This means it will not return to its original shape after removing the load. So next we come to the curved upward region. After yielding, here it is yield point, the material enters into plastic region, and here deformation increases rapidly with small increase in stress. This curve continues to rise until it reaches the highest point, which means here. Called this point is called UTS, which means ultimate tensile strain. In this graph, here's the rise in the curve, and this point is called UTS. This is the maximum stress the material can withstand. So here's the maximum strength, which means here it is the UTS. Next, then point to necking. After UTS, necking begins. After the specimen undergoes ultimate tensile strain, it begins necking. In this stage, cross-sectional area reduces at one point. Here necking begins. Now, after necking, finally the material breaks at the fracture point. Here it is the fracture point, which means here. Stress decreases because the area reduces significantly and the specimen ultimately fractures. Next, these images show how the specimen changes during the test. Initially it has here initially it has a uniform shape. During plastic deformation, elongation increases. During necking, the middle portion became thin. Finally, fracture occurs. Here, fracture occurs. The, en- the entire curve helps us understand the elastic behavior, plastic behavior, and the maximum strength and failure point of material. Now, let us discuss the regions of stress strain curve. There are two main regions in the curve, the elastic region and the plastic region. First, we see about elastic region. In this, in this graph, it is a elastic region. Here, the material behaves elastically and follows Hooke's law, which states that stress is directly proportional to strain. This is why the graph is a straight line in this region. Next, we see the plastic region. Before going to the plastic region, the slope of the straight line portion represents Young's modulus, which indicates stiffness of the material. So next we see the plastic region. Here's the plastic region. After the yield point, the material enters into plastic region. In this region, deformation become permanent. It means the material will not return to its original shape even if the load is removed. So next, let us see their mechanical properties. From this curve, we can determine several important properties of a material. First, we see the Young's modulus. It is a slope of the elastic region and represents the stiffness of the material. Second, yield strength. This is the stress at which plastic deformation begins. Third, ultimate tensile strength or UTS. This is the maximum stress the material can withstand before necking. We can also determine ductility, which indicates how much the material can deform from fracture. It is usually measured in terms of percentage elongation. Finally, toughness. Toughness is the ability of a material to absorb energy before fracture. It is represented by the total area under the stress strain curve. Next, we see their applications. It is widely used in design, structural design to ensure buildings, bridges, and can safely withstand loads. It is also important in designing machines components like shaft, bolts, and gears. And the curve helps engineers in proper material selection based on strength and ductility requirement. It is also used in safety analysis to prevent material failure by choosing an appropriate safety factor. Finally, I conclude that the engineering stress strain curve helps us understand how material behave under applied load and plays a vital role in safe and efficient engineering design. Thank you.